Next, we're going to take a look at some more examples of product and quotient rules. One of the things that you'll notice is that product and quotient rules, we are going to be practicing a lot of the skills that we already used, looking at power rule and some of the other derivative rules that we've already seen. So all of this is just building on itself. For our first example, let's look at the derivative of, I'm missing a parenthesis here, pardon. The derivative of the square root of x plus 3 times 4x to the 2/3. And before I start computing this derivative, I don't like square roots because it's hard to do power rule on something that has a root sign. So instead, I'm going to rewrite this problem so that instead of having a square root, I'm writing this as x to the 1/2. Because square root is just saying x times x equals, the square root of x times the square root of x equals x, or in other words, x to the 1/2 times x to the 1/2 equals x. So this is just another way to rewrite the exact same problem. And the reason why I rewrite it is because now it's going to be easier to employ our product rule. So recall the product rule is first times the derivative of the second. So I'm going to start by just writing out my first function. My first function is x to the 1/2 plus 3 times the derivative of the second function. In this case, I'm going to have to use power rule. So I take this coefficient and put it down front. So this is going to be 2/3 times 4 times x. When I subtract 1 from 2/3, I'm left with -1/3. So this is first times the derivative of the second, and then I have to add on the second function, which is 4x to the 2/3, times the derivative of the first function. And again, I'm going to use power rule. So by power rule, this 1/2 comes down in front, and it becomes 1/2 x to the -1/2. And what happens to this term when I take the derivative of this term? The derivative of the constant 3, I can think of this as a line with slope 0, and so this is just going to become 0. Now, this looks pretty complicated, and in general, it's okay not to simplify this. Sometimes we do need to simplify it to get a correct answer. I'm going to simplify this a little bit, but I'm going to leave it written out so that the fact that we used product rule is still really clear. So 2/3 of 4 ends up being 8/3 x to the -1/3 plus 4x to the 2/3 times 1/2 x to the -1/2. I can combine these two terms and I get 2 as my coefficient. And how do I combine x to the 2/3 times x to the -1/2? You know, I might just leave that written out. That's a review example. Really what we would have to do is I would have to take 2/3 and subtract 1/2, and that's going to be the exponent on my x. And I would have to do subtraction of fractions by getting a common denominator of 6 and then subtracting, which is what, anyway. So that's my first example, and I'm going to leave it unsimplified, in part to help illustrate that it's okay to not simplify your work when doing problems. That's one example. Let's look at another example. Let's say we want to take the derivative of e to the x plus 2 divided by 3x squared plus 1. So again, before I start taking the derivative, I notice that this is a quotient, so I'm going to have to use quotient rule. And instead of looking at this, I'm going to rewrite the numerator. So this is the same thing as the derivative. Recall, this is e to the x. How many times am I multiplying e by itself? I'm multiplying e out x times, and then I'm multiplying it 2 more times. Or in other words, that's the same thing as e times e, or e squared, times e to the x. And the reason why I rewrite this is that now I notice that the e squared, this is just a constant. This is a term that I can pull out front, and I don't have to worry about this term. And the e to x term is something that I know how to take the derivative of. So this is 3x squared plus 1 on the bottom. So let's go ahead and employ our quotient rule, which is bottom times the derivative of the top, and our bottom function is 3x squared plus 1, and the derivative of our top function, the derivative of e to the x is e to the x, and this coefficient just goes along for the ride. We don't have to do anything, because if there was a 2 out front, for example, it would just go along for the ride. X squared e to the x. So that's bottom times the derivative of the top, and then I'm going to add the top function times the derivative of the bottom, and again we can use power rule and take the 2 down, so I get 6x, and the plus 1 becomes 0 because that's a constant function. All of this is divided by the bottom squared, 3x squared plus 1. And again, I'm not going to go through the work of simplifying this, in part because this is really clearly demonstrating what the quotient rule is. And if I did ask you to simplify it, we could simplify it. Notice that we have a common term here that we could factor out. We could distribute everything across if we wanted to. Instead of, oh, the bottom squared. Sorry, I'm glad I caught my own error. That's an important part of quotient rule. It's not just divided by the bottom, it's divided by the bottom squared. Finally, we're going to look at one more problem. This is a little blurry, but this is the derivative of e squared times 3t to the fourth. And this looks like a product rule because I have the e squared here and then I have this term here. But notice, this isn't actually the product of two functions of t. This is actually just a constant. E squared is actually 2.7 blah 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 squared, and if I plug this into my calculator, I could see here here that e squared is actually just a number, 7.385 blah blah blah. And so this isn't, I don't actually need to use product rule for this. This is a trick question. That this is actually just, if I took my e squared and multiplied it by a 3, that would be my coefficient out front is just 3e squared. And I can use power rule and take the 4 down, t cubed. And this is my final answer. So I could rewrite this as 12e squared t cubed. And this is a function of t because e is just a constant. However, let's say I didn't notice that, and I wasn't paying attention, and I decided to do product rule anyway. What happens if I decide to do product rule on two things where one of them is not actually a function of t, it's just a constant? Let's see what happens when we do that. So I'm going to rewrite this, e squared times 3t to the fourth. Let's recall our product rule. Our product rule is first times the derivative of the second, so it's going to be e squared times the derivative of the second is 12t cubed. I did part of that in my head. The 4 came down and multiplied by 3 to give me the 12, and 4 minus 1 is my power on t, which is 3. So that's first times the derivative of the second, plus second, which is 3t to the fourth, times the derivative of the first. But notice there are no t's here. This isn't an exponent, this isn't e to the t. Because there are no t's here, this is a constant, and the derivative of a constant is 0. So because of that, we see that this second term is actually just equal to 0, and my derivative becomes e squared 12t cubed, which is exactly what we saw up above. So even if you do apply product rule, it'll give you the same answer because the derivative of that constant is 0.